This is Team Ends with Dr. Rashidi's Design and Manufacturing class.
The human knee is a triumph of design. The knee joint, which evolved from our common ancestor, the chimpanzee, to accommodate bipedalism, contributed to our success as a species. The biggest joint in the human body, the knee, enables almost all forms of human movement, from walking, running, jumping, balancing, and even standing still. The age of patients is getting younger, and people are living more active lives. Keeping this audience in mind, our engineering team here at Needful Replacements has created a total knee replacement for active adults, which does not require the removal of healthy ligaments and utilizes a mobile bearing design, cobalt chromium bone components, and a polyethylene plastic spacer. Every decision for this product, from the materials to the manufacturing, was made according to design for quality and manufacturing, as well as compatibility with a healthy active adult. Now, the engineers here will give a brief overview on the design decisions for this product.
The knee acts as a type of hinge joint known as a synovial joint. Back and forth motion, known as flexion and extension, is allowed, but very little horizontal and side-to-side movement is supported. In a synovial joint, the cavity of one bone fits inside the other. The synovial membrane, a fluid-filled sac which lubricates and protects the joint, makes the knee almost perfectly frictionless, a feat which is difficult to replicate artificially. The patella protects the synovial cavity along with the meniscus and bridges the upper femur bone to the lower tibia bone. These parts together, along with cartilage and fat, enable the human knee to have all 6 degrees of freedom: superior and inferior translation, flexion and extension, vargus or valgus rotation, axial rotation, medial or lateral translation, and anterior or posterior translation. The knee can also support forces and torques that are many multiples of one's body weight. A well-designed knee replacement can support these movements and withstand stress from these loads without wearing down too quickly over time. Given the great importance of the knee, it is catastrophic when the joint begins to degrade. Osteoarthritis, or OA, is one of the most common causes of knee degradation, in which the tissues in the joint break down due to wear and tear over time. Full knee replacements are needed for those who suffer from OA, who are typically older individuals. Approximately 790,000 Americans receive knee replacement surgery every year, and these patients are becoming younger and more active on average. Leading the market in knee replacements are companies like Zimmer Biomet, Stryker, Smith & Nephew, Exactech, and more. From improving upon the range of motion, lengthening the period between knee replacements, shortening post-op recovery time for patients, and creating software which generates patient-specific 3D printable knee replacement models, companies have shifted away from mass production to patient-personalized replacements. Experimentation in manufacturing methods, which now include additive manufacturing, and materials research, which has expanded the range of knee replacement types and biocompatible coatings, have fundamentally changed the knee replacement market. Demand for a knee replacement for osteoarthritis patients who lead an active lifestyle is growing. The knee replacement design showcased in this video is designed for the increasingly active, increasingly youthful demographic of patients.
The design we are talking about today is a mobile bearing full knee replacement. The knee replacement starts with a series of precise cuts on the femur, tibia, and patella to remove the damaged bone material. Then the femoral component is inserted into the femur and locked in place with either cement or, as in our design, a porous surface finish is used for the bone to grow into. This process is repeated with the tibial component and patella as shown. Finally, the plastic spacer is inserted into the tibial component, but is not cemented or fixed to the tibial component to allow for it to rotate with the femoral component as the knee rotates and moves. This is the difference between a fixed and mobile bearing knee replacement. The fixed design's plastic spacer is fixed to the tibial component, preventing the plastic spacer from rotating with the knee. The femoral, tibia, and patella components are made of cobalt chromium to allow for a frictionless rotation against the polyethylene plastic spacer. This will simulate an actual knee's range of motion and functions. The reason for the mobile bearing design is to accommodate the more modern patients of knee replacements who are tending to be younger and more active on average. The mobile bearing design is designed to simulate more of the 6 degrees of translation and rotation a regular knee has. This will cause less wear and fatigue over time, and in turn creating a longer lasting knee replacement. A fixed design can cause greater wear and forces on the plastic spacer due to when the knee and femoral component try to rotate, it causes stress concentrations on the plastic spacer as shown. However, the mobile design rotates with the femoral component and allows greater contact area between the two components, and in turn, less stress and fatigue on the plastic spacer. Mobile models are also rated higher in terms of knee score and function score. Knee score assesses the knee itself, considering pain, stability, range of motion, and alignment of the knee. It also specifically designed to evaluate the knee's mechanical functions. Function score evaluates the patient's ability to walk, climb stairs, and reflects the overall functionality capabilities of the patient. Another study by Dr. Fisher and McEwen shows that a mobile bearing design results in approximately 5 cubic millimeters of wear per million cycles versus 22 cubic millimeters of wear per million cycles for a fixed design. Another aspect of our design is not utilizing a cement to attach the femoral and tibial components to the bone. Instead, we will utilize a rough and porous surface finish on the undersides of the material to allow for the bone to grow into the knee replacement. This will allow for a sturdier and longer-lasting knee replacement connection to the bone.
The plastic cushion is made of high-density polyethylene, which has low friction and is biocompatible. This is used instead of a metal spacer because when two metals rub against each other, it tends to cause increased scratches and microfractures, and due to the spacer's constant contact and rubbing against the metal femoral component, polyethylene is a much better alternative. Polyethylene is challenging to manufacture using common 3D printing options, like fused deposition modeling, in which plastic is extruded into freestanding layers. This is due to its high thermal expansion coefficient, making it prone to warping during processes using heat. It also has low surface energy, meaning it is difficult for its layers to adhere to each other. Therefore, we have decided to employ injection molding as the means of creating the plastic spacer. This process uses heated plastic powder, which is moved via a motor into a mold. This way, there is no room for warping and layer adhesion is not required. The mold is created from a 3D printed wax. The mold allows the polyethylene to be created so that it slips smoothly into the tibial metal component. Hydroxyapatite is used to coat the polyethylene that mimics the mineral of the bone, allowing for smooth interactions between the bone and the implant. The chosen implant also preserves both the anterior and posterior cruciate ligaments, such as ACL, aiming to provide a more natural knee motion. This is more suitable for patients whose ligaments are healthy. The femoral and tibial component are typically made of cobalt chromium or titanium due to their scratch resistance, high corrosion resistance, high durability, and being biocompatible. Our design utilizes cobalt chromium since it has a higher strength and wear resistance, therefore being better for undergoing cyclic loads and stresses that come from exercise.
As you can see, our product has successfully focused on addressing the needs of younger, more active patients. The choice of materials and the shift from fixed to mobile bearing designs have been made with durability and lots of natural movement in mind. The design shown emphasizes the use of cobalt chromium for strength and wear resistance, along with high-density polyethylene spacers to reduce friction. It employs injection molding for manufacturing due to 3D printing limitations with polyethylene. This design aims to preserve natural ligament function with a focus on mobile bearing design for improved long-term outcomes and patient satisfaction. Thanks for watching.